Hello, I'm Brianna Rodriguez, and I'm a senior undergraduate mechanical engineering student.
Hello, I'm Andy Kapperman, and I'm also a senior undergraduate mechanical engineering student. And we are both from the University of North Florida's College of Computing, Engineering, and Construction, or the UNFCCEC. We have been working with Dr. Cheatham Akan, Assistant Professor of Civil Engineering at the UNFCCEC, to prepare this presentation for you. Together, we have all been a part of the U.S. Department of Energy Marine Energy Collegiate Competition, Powering the Blue Economy, a competition that challenged us to come up with a marine energy solution. On today's presentation, we will be talking about wave energy converter development and the environmental considerations that go into their design.
Just to give you guys just a brief overview of the topics we're going to talk about in this presentation, we're going to start off talking about wave energy converters, different types, how they work, some design considerations and environmental considerations. And then after that, we're going to talk about the WEC design University of North Florida has, and that goes into the small scale design and the intermediate design.
The topic of today is wave energy converters, or WECs, sometimes abbreviated to WECs. And to keep things short throughout the presentation, we will often refer to them as WECs. WECs, in short, are devices that enable us to capture the energy of a wave and convert it into electrical energy that we can use in today's power grid. They can be divided into a couple of different types, the first of which is a point absorber. Here we have an image of the PB3 power buoy point absorber. And if you're looking at it, it kind of looks just like a normal buoy that most people are familiar with. And in essence, many designs actually are. The key point with point absorbers is that they are small. Just like a buoy, a wave can come from the left, from the right, from the back, from the front. It doesn't matter. It still moves up and down. And that's the key advantage with point absorbers. They're small with relation to the size of the wave. The second type of wave energy converter is a terminator. And the name doesn't come from the movie. It comes from what it does to the wave. In this image, we have the Salter's duck terminator, and we've got a wave coming in from the left side. And then it comes into contact with the device, and it kind of pushes it up. And that motion is where we capture the energy. But once the wave moves past the terminator, the wave will actually diminish in size. And so it in essence, terminates the wave. Terminators sometimes come in the shape of a flap that's put in the water that's moved with the motion of the waves, or in this case, a guitar pick shaped device that gets pushed up as the wave moves and approaches toward it. The third type of wave energy converter is a wave attenuator. Wave attenuators are connected in segments, and they kind of ride on the top of a wave, and it looks a bit like a snake, so to speak. And so it moves with the crests and troughs and wiggles like a big chain. And in those joints, that's where we capture the energy. And the key thing with wave attenuators is that their axis is parallel to the wave. The wave direction moves along the length of the wave attenuator. Now, with a basic understanding of what the different types of wave energy converters are, let's talk about how exactly they go about converting that electricity and the different ways that they operate. The first of which is through flexing. Wave attenuators and wave terminators are both typically operating based off of the flexing principle. It has to do with sometimes sections resisting bending, as in the wave attenuator. Remember that snake sitting on top of the water? As the different sections move with the waves, the joint there is where we capture the energy. Sometimes it's movement along a hinge. Down here we have an image of the flexing operating principle. We've got a big panel under the water, and we have a hydraulic link connecting it to the sea floor. And as the panel moves left and right, it extends and compresses the hydraulic arm. Oftentimes, the electricity is generated through the use of an oil hydraulic power system. Next, we have bobbing. Bobbing is the common form used in point absorbers. The float moves up and down with the wave, and that may be paired with pumps or magnets in order to generate electricity. Next, we have overtopping. If we take a look down here at figure 6, this illustrates what overtopping is. The way it works is water will be forced up along a ramp, as kind of shown in the picture. And after it passes over the ramp, it spills into a reservoir, after which it flows through a channel. Usually there's a turbine mounted in the channel. And as the water moves downward back to the body of water it left, it flows past the turbine and spins it, generating electricity through the use of a hydraulic turbine. After that, we have the oscillating water column. Now, this one is kind of akin to whenever you wash dishes and you put a bowl upside down, and then when you tip it up, you hear the glub, glub, glub of the water leaving. Well, imagine you don't let the water leave. You just put the bowl upside down in the water. And then as waves approach the bowl, it moves the water under the bowl up and down, and it compresses and decompresses the air that's been trapped under the bowl. Same principle with the oscillating water column, except on a larger scale. And the way we capture the energy is that air that's trapped under the bowl. What we do is we force it through a channel, and in that channel, we have an air turbine. So as the wave moves up and down, and it compresses and decompresses that closed chamber of air, the air is forced in and out of that air turbine, which spins and generates electricity. And a quick note on the turbine type, often the turbine that is employed in oscillating water column wave energy converters is a Wells turbine, because the Wells turbine can actually spin when air hits it from either direction. So you capture energy when we compress the air and when we decompress the air.
Now that we know how the WEC functions, let's talk about how they're designed. As marine energy gains popularity in the power industry, we need to design devices that last. One important consideration is material recyclability. We're putting these devices in the ocean and we want to minimize the potential waste and hazards in the water. Thus, putting materials that can be recycled at the end of the device's life is key. The next factor that impacts the device's design is corrosion. Since WECs are submerged in the ocean's waters, corrosion of material naturally occurs. Corrosion is defined as the deterioration of material due to chemical, electrochemical, and other reactions of exposed material in its environment. High salinity, varying temperatures, and humid environment from the seawater exposure are some factors that create a catalyst for corrosion to occur. Two types of corrosion that we'll be looking at is uniform corrosion and pitting corrosion. Uniform corrosion is the most prevalent type of corrosion. It's defined as uniform loss of the material due to a corrosive environment, and figure 8 is just a prime example of that. Pitting corrosion, on the other hand, is loss of material at specific small parts on the object. Pitting corrosion creates these little pits or cavities in the material, and they come in all different shapes and sizes. The small grooves seen in figure 9 are instances of pitting corrosion. Corrosion impacts the device design by limiting the materials that can be selected. High stresses can occur in these pits and cavities and can lead to possible material failure. This can be water leakage, potential breakage of components, and many other things. This limits our metal selection to non-corrosive metals. Some examples of these metals are stainless steels, copper-based alloys, nickel-based alloys. But one thing to note with these metals is that they're very expensive and they will increase the cost of manufacturing. Another solution is to use protective barrier coatings on the device material. These coatings work as a sealant to cover the entire exterior of the object. Protective barrier coatings like powders, paints, or plastics increase the longevity of the device's material while keeping manufacturing costs low. Another factor that impacts the design of a WEC is called a power takeoff system. PTOs take the mechanical forces and motions from the waves and convert them into usable energy. When designing, there's two options you can select from: hydraulic motor-based PTOs or direct electrical drive PTOs. Hydraulic motor-based PTOs are great for converting slow oscillating motions into energy, which means they handle small waves really well. They're highly efficient systems, but they do have a short lifespan. They have many moving mechanical parts, and those are susceptible to failure and have potential oil leaks, which is not what we want in the ocean. The other option is direct electrical drive PTOs. This PTO transfers wave energy directly into electricity. It uses a linear generator, which is just a little linear motor to generate electricity. All the design components are a little bit bulkier and does mean that the final design will weigh more. Another thing to note is that this PTO has a fluctuating voltage due to irregular waves, which means it is a lower efficiency compared to the hydraulic based system.
Now that we know what wave energy converters are, how they operate, and some of the design considerations, let's talk about actually keeping them in place. And we do that with a mooring system. Some key components of a mooring system include the anchor, which transfers forces to the seabed, the mooring lines, which link the wave energy converter to the anchor. It's the cable or chain that sits in the water and connects the top to the bottom. And then we have the connections, which are the points, the loops or the hooks that connect the cable to the wave energy converter into the anchor. There are a couple different possible configurations of mooring. We have a single line that connects the anchor to the wave energy converter, or a spread system where we have multiple lines. We have tension, where the wave energy converter and the line is very tight and there's not a lot of up and down movement allowed, or we have slack and catenary systems where there's some movement allowed. You can go up and down. And which one you choose will determine how much movement is allowed. When choosing what kind of anchor, mooring line, or connection you're using, you have to keep in mind the conditions that you expect. You have to keep in mind what sort of movement you're going to allow. And if you're using multiple units in an array, you have to keep in mind how one unit will interact with the wave, how that wave will be impacted by that movement when it hits the next unit. Also, if you're needing to remove one unit from an array, is it still possible with your current mooring configuration? Here's an image of the Polaris wave attenuator that we talked about a little bit earlier. They're using a spread system because they have multiple mooring lines, and they're using a slack system because those lines aren't tight.
Another key factor to keep in mind throughout the design process is the variability of operating in different conditions. These WEC devices ideally should work based on different wave amplitudes. It should be able to produce power off of big waves and small waves. These devices should also account for varying wave periods. It should work when the waves are coming fast and high frequencies, or even just slow and low frequencies. And lastly, the device should be built to withstand a variety of weather patterns. Out in the water, it's at the mercy of Mother Nature. Some days she'll give you some great, beautiful weather, and other days she's just going to rain down hard on you, and you should be able to last through it. Lastly, while in the design process, one should consider the maintenance of a device. How often will somebody have to go out there and check up on the device? We know periodically someone will have to go see if there's any water leaking into internal components, if the device has shifted off of its mooring axis, or to just check if any artificial reefs have developed around the device. We want to avoid WEC failure and protect the environment simultaneously. So these are factors to keep in mind while you're going throughout the design process.
Now let's talk about environmental considerations. Wave energy converters are great in that they generate clean energy from the ocean. However, it's important to make sure that that energy does not come at the expense of our oceans. The first environmental consideration is biofouling. Biofouling is when the growth of a living organism on a mechanical system impairs the operation of that system. For instance, let's say we have a point absorber that's supposed to be bobbing up and down, moving a shaft in and out of a housing. If barnacles start to grow on the shafts, that's going to make movement very difficult, and those shafts won't be able to move as we expect them to. Besides obstructing movement, another impact of biofouling is making inspections difficult. If there's ever a problem with a WEC, it is difficult to just visually find the problem if it's covered in growth. The next thing is fatigue. If we have organisms growing on a WEC, they're going to be carrying out chemical processes right on the WEC surface, potentially causing the materials to corrode. And that's on top of the corrosion from the salt water that we were talking about before. All this corrosion could potentially lower the fatigue life of the device. And finally, increased loading. If we have a bunch of things growing on the device and we have water moving past it, the device now has an increased surface roughness. As water moves past and against the rough surface, it will produce more forces, increasing the WEC's external loading and potentially increasing the stress on the mooring system. In short, things growing on a WEC create lots of problems. Here's a quick summary of the key environmental considerations. We have corrosion, like we discussed before. Salt water, unforgiving, and can compromise the WEC's operation. If part of the wave energy converter rests out, disappears, we could have parts breaking off. We could have operation totally impaired. Biofouling, if artificial reefs start to grow on it, it can hinder the operation of the WEC. Just general awareness of the environment that the wave energy converter is going to be operating in. We have to account for changing tides, extreme weather. You need to understand what sort of environment you need to be able to withstand for long periods of time and be able to design to endure through any difficulties you may encounter. And finally, marine life. You don't want the wave energy converter to cause trouble for marine life or for the marine life to cause trouble for the wave energy converter. Maintaining the safety and well-being of the marine life is of utmost importance. And we also do not want to pollute the oceans by using a wave energy converter. And all of these key considerations can be accounted for in design by choosing good materials, using appropriate coatings, and mooring the wave energy converter correctly.
Now that we know what a WEC is and how it works, we would like to introduce you to UNF Crew's Wave Energy Converter. We are generating cheap renewable energy from waves. First, let's talk about our small scale design. We built a small WEC to test the optimal setup for power output. The UNF crew made 3 small prototypes, Jimmy, Timmy, and Kimmy. These 3 prototypes were all point absorber WECs and can be seen in the Emmy family tree. Each WEC was just a little bit different than the last. 2 of the WECs were made by 3D printing the exterior. The computer model on the right is the exterior that was printed for these devices. One of them was made out of PVC pipe and PVC sheets. Each device had a varied number of coil turns and gauge wire thickness. Changing these parameters impacted the power output from each WEC. A LED strip was used to measure the power output. If it lit up the device, it was working. If it didn't, we would just make a new prototype to improve its design. Once we proved that this design worked, we moved on to the next step, the intermediate WEC design.
And finally, for the intermediate scale design of our wave energy converter. After we had success with the small scale design, it was time to move on to a larger scale. Here's our intermediate scale design. This phase of development essentially combines 4 of the small scale designs. We have 4 of the small WECs inside of a larger housing and a larger float on top. As a wave moves past the point absorber, it'll move that float up and down and translate the motion to the 4 wave energy converters inside the larger housing. The float at this point is manufactured out of PVC, and all the electrical components are located inside that larger housing down at the bottom. In total, it weighs about 25 pounds. At this phase of development, we are nearly complete with the manufacture of the intermediate scale design and are poised to begin testing later this year. It's been an extremely exciting project, one where we're learning a lot, and all the design points that we've discussed in this presentation, we're keeping them in mind as we continue forward in the design process and moving ahead to large-scale designs and testing. It is our goal to keep the environment at the forefront of our mind as we move ahead.
Thank you for listening and learning about wave energy converters. We may not know all the answers to your questions, but this conference did allow us to open up a discussion about wave energy and its potential impact.
And it's important to remember that while we've talked about a lot of things to keep in mind when designing them, wave energy converters have a tremendous potential. They serve as a viable alternative to using fossil fuels, which we heavily rely on at this point in time. It's possible that by keeping the considerations that we've talked about in this presentation in mind when designing, manufacturing, and deploying wave energy converters, we can generate electricity in a clean and responsible way.
Before we go on, we would like to extend our thanks to the UNF CCEC, the U.S. Department of Energy Marine Energy Collegiate Competition, Powering the Blue Economy, for their help in sponsoring this research, the Taylor Engineering Research Institute, and of course, Dr. Chida Makan. Dr. Akan has been there through thick and thin with us, answering questions, providing feedback, and just being a great mentor. To everyone, we couldn't have done this without you. Thank you so much. These were some of the references we used. Again, thank you guys so much for having us. Truly appreciate it.